So let's start with this one. And last Friday we have done this about the three quarters, but let me quickly overview what we have done. So this section is about the base excitations. So last week we have pretty much reviewed for the base excitation. We assuming the base is not fixed, but it have oscillating at the functions of y sine omega t. Okay, so basically that's a harmonic oscillation on the base. And the equation of the motions, by considering the base excitation, basically we have this form. Okay, so y dot representing the dynamics of the ground. And then we come up with the formulations. And here we have a few scenarios. The first one we look at is the displacement transmissibility. The displacement transmissibility, by definition, is this term. Basically, is the ratio of the displacement of the mass block to the ratio of the base, and that is what we defined for the first term here. Okay, and this curve characterizes the this equation here. Okay, and this is the phase angle. The phase angle we simply summarize into this form. The second one we concerned with about the magnitude of the steady state accelerations, and so that means we want to determine is what is the magnitude of the accelerations of this term, and then assuming no, that's not assumed. We have a steady state displacement, then we simply take the double derivative. Then from here you can see that once we take the double derivative, this term will become minus omega squared times x, etc. So that is equal to this term. Okay, so compared to the displacement, we simply multiply the minus omega squared. That gives us the magnitude of the accelerations. So again, we simply multiply this constant, and that will give us the magnitude of the accelerations. So in this way, from the previous page, we have displacement information is this one. So the whole term is scaled up by that constant, which constant? By this constant. Okay, so again, the previous term multiplied with omega squared. Here we take about the magnitude, so we can drop the negative sign. So only concerned about the magnitudes, basically we scaled up the previous page, the displacement with these numbers, okay, and we redo everything. So this term is about the magnitude, and that is the equations for the magnitude of the accelerations. Okay. The third one, force transmissibility. The force, what is a force? And the force being transmitted from the base to the machine or to the whatever the object we concerned. So how much force being transmitted, you can see by looking at this diagram here. The force will be responsible, that is due to the deformation of the spring, and also due to the relative displacement between two ends of the dampers. So the forces are basically the two terms. Okay. So in here we talk about the force transmission. Basically we're concerned how much the pure force is being produced. And by looking at the original equation of motions, and that is the two terms, summation of the two terms give us the force. We're concerned about this force. Okay. So again, by looking at this equation of motion, basically the force being transmitted. If you remove this term to this side, basically the force being transmitted is equal to minus m omega double dot. Okay, so this term is pretty straightforward, obtained by looking at that equation of motions. Okay, so that is summarized here. Again, the force being transmitted is related to the accelerations of the performance of the steady state displacement. So again, here in the previous page, we have obtained the accelerations. Okay, so we can look up here. In the previous page, the acceleration has a magnitude equal to this. So omega squared multiplied with something. And then the force is simply equal to m. We simply multiply additional constant. So basically we'll look at this form here. The magnitude simply is this form. Okay, so we based upon this one, we manipulate a little bit. So in this way, the force transmissibility is defined by the ratio of the force being transmitted to the ky. This is the spring constant multiplied with the amplitude of the base excitation. So that is our definitions. So we plug in everything here, and then the x over y. What is x over y? Again, from the previous 2 pages, we have this one here. So this is information about the displacement. Okay. So we pick up that information to here. So we plug in everything here, and we do a little bit arrangement. Here, the k. If we move the m to the denominator here, basically m over k or k over m here equal to omega n squared. So this whole term is actually equal to this one. Can you see that? M omega squared divided by k. This one is equal to omega squared, and then we move the m to the denominators here. Okay, so this one is equal to omega squared, and this one actually is our natural frequency squared. So the whole thing basically is equal to r squared. Okay, so basically here the pre-multiplied this kind of constant is equal to r squared. Okay, and then basically everything can become like this. And for so for this, and that is we define as a force transmissibility, and that categorized in this curve. And this curve is a little bit messy, okay? But here I try to get everything. And this the ratio, the phase angle basically is propagated the same as we had before. Again, that is everything kind of derived from this term. So this angle should be with the same as that one. Okay, so that is the 3 portions we've seen last week. So I do this a little bit quicker. So today we look at the fourth one, and this is the relative displacement. And relative displacement, that is defined by this page summarize the whole result, and we can go over this. What is the relative displacement? And that is defined as the displacement of the end relative to the base. So, which means here we define the relative displacement by this. With using the notation zt, okay, and zt is a relative displacement of the end to base, so that is xt minus yt. And this is our definitions. Okay, so with this one, and you might consider why we want to come up with this one. And there's a reason here. And today we have applications about the different sensors. And one of the sensors is the accelerometers, a sensor to measure the accelerations. So that one we're going to based upon these definitions here. Okay, so here is a summary. So the relative displacement transmissibility by definition is z over y. So here is the summaries. And again, this curve, this formula is we can feature it by those curves here. So let me give you a little bit the derivation here. So from our equations of motions, and that is mx double dot plus kc minus y dot plus k x minus y equal to 0. Okay. And we modify the equation of motions by doing this. So if because here I want to come up with these terms. So this term basically appear here and derivative appear here. So double derivative, we can make a one term. So that means here let me minus my double dot and making the both sides imbalance. So this one is I also minus my double dot. Okay, so by artificially adding this single term on the both sides, then we can come up with this. That is mx double dot y plus c plus k equal to minus y double dot. Okay. So what is y double dot? And here we are given the y is the information about the base. So that is information. So y t equal to y sine omega t. So that's the given. So therefore, this term we can take double dot. So here we can become mz double dot plus cz dot plus kz will be equal to minus n. And then we can take the double derivative on the input here. So that will be equal to m omega square and y and sine omega t, and this term no negative. Right, because the double derivative of the sine function is equal to minus, so this term after derivative will have a minus out, and minus with a minus basically become a positive term here. Okay. So from here, if you can see, basically this compared to our template. So here we compare to our template. Let me write a template. We have a template mx double dot plus cx dot plus kx equal to f now and sine omega t. So this term has been appearing very early, right? Do you remember this term? That basically, what is this term? This term basically coming up is from here. We have the systems and damping ratio, and we have the mass. And this one is subject to, this is the degree of freedom. This one is subject to the loading, and loading Ft equal to F now and sine omega t. Right? So if you remember this one, that is from the very beginning of these chapters. We talk about the transmissibility. So basically, if you remember that one, x divided by delta st equal to 1 minus r squared plus 2 zeta r squared. Right, so that is a piece of information we've been using from the very beginning. I believe that is the first portion of the homework, the first homework in these chapters. Okay, so we compare to this one, you can see basically from here, if we're using this as a template, so basically this result you have is the z. We borrow this one and the magnitude. What's delta st? So let me spell it out. Delta st equal to, what is delta st? Do you remember? We call it static deflection, the magnitude of the force divided by the spring constant. Right? Okay, so we borrow this template, and then you can see, so this is our equation of motion for the displacement, for the relative displacement. So from here you can see this term is our F now. So if we compare the term by term, this actually is our definition of the F now compared to this one, right? Okay, so we can write it up. So the magnitude of the degree of freedoms here the degree of freedom is Z. Okay, so we let Zt equal to Z, and this is the sign, omega t minus V, okay? So this is the magnitude, and divide by, compared to this one again, the what is F now corresponding to here, so that is m omega square y, and that is the our F now in this formulation divided by spring constant K. Right, so this term is equal to this one. 1 minus r squared plus 2 zeta r squared. Good? Okay, so now we have this one, then we look up our definitions. Definition for the relative displacement transmissibility, that is Z divided by Y. So based upon that one, we try to formulate what is Z over Y. So I want to formulate Z over Y, so therefore Z over Y, by definition, by follow up this one, I simply move the remaining term to here, so that is m omega squared divided by K, and then divide by the same thing, the same denominator here. Okay. And again, if you look up that term carefully, the denominator and the numerators, let me write up here. So m omega squared divided by K equal to omega squared K over m. Okay, so this one is equal to omega squared, and this is a natural frequency square. So basically, the numerator is equal to r squared, and denominator is the same. Okay, so hopefully, yeah. So basically, that is this term here. Okay, good. Again, for these chapters, very important because these chapters serve as a base for force excitations and what kind of force? Harmonic force. And here, in terms of harmonic excitations, that including the very original, we apply the force to the mass block, or vice versa, we have the force being applied through the basement movement. Okay, so basically in these chapters, quite a few, I would say, variations from the standard template, and that is the applications. Okay, so that is theoretical descriptions of the different scenarios, and based upon this one, we have quite a bit applications. I want to emphasize on applications. The first application, anyone can remember? Have you been exercised in your homework? What will be the first application we've seen? Vibration isolations, right? Okay, so I will give you one bonus point to the test 2. Anyone else want to try any other applications? Or you can think about beyond the scope. I will give you more. Any more you've been exercised at least on the homework? Any applications? Which means some kind of say some. Anyone want to try before I try? I give myself no point. You can leave the chance to other people. I know you can. We have one homework due today, right? End of the day today. And what is the topic you are right now exercising?
Transmissibility.
Transmissibility. Transmissibility of some. Okay, so that's a 1. Okay. And for the homework 8, we have one more homework due this Saturday, the end of the day, Saturday this week. So have you any chance to look at that homework yet? So what is the topic on that one? Probably not. And give me a few minutes, and we're going to go over that one. Okay. So that is, I would say here, I kind of give you the hint how to prepare for the test 2. And I think the test 2, I will put the description, the problem design toward the applications. So which means you need to know how to apply the information, so much information, to the right categories. Okay, this page basically summarizes the base excitation only. Okay, for the base excitation, how many scenarios? The first one, we talk about the displacement transmissibility. We have such curve. And for the displacement transmissibility, we define is this. The displacement, the ratio of the displacement of the mass block to the magnitude of the base. And the second one we talk about is the force transmissibility, and that is the definition here. And here I'm using the colors to highlight the difference between the two functions. Okay, so basically the summaries, and basically this is simply r squared multiplied with this one. Okay, and that curve looks like this. Then we talk about the relative displacement transmissibility, that by definition is this one. So again, that curve is like this. So you can see the three different kind of categories based upon the excitation, the base excitation, they have a different form. And here I would say this page will be more useful for our calculations, okay? And so I kind of summarize in here. And if you look at this carefully, basically the curve about the transmissibility, they are different. They are different. Pay a little bit of attention on the details here. Okay, and here we can look at one example.